All right. So the goal, as we've talked about already, is statistical significance. Now we're going to find out what that actually means in words. So the null and alternative hypothesis help you set up an experiment, and so that you're answering the right question and you're thinking about it the right way and with as little bias as humanly possible. So the goal is to prove that something is statistically significant. This means our results were extreme enough that they likely did not occur by chance. And you quantify this using something called p-values. So I made up some stupid little example because it was simple, and then I'm actually going to show you a real example with A/B testing. So silly hypothetical example. In the US, the height distribution for men is shown on the right. This is the actual distribution. So the mean is 5'10", and the standard deviation is 4 inches. So when you look at this, this is what it means on the normal distribution. I need to get one of those little things where when you click, it shows, but right here, I'll try to make it real obvious. So if you are 6'6", that means 97.5% of individuals have a smaller height than you. So this would put 2.5% would live there. So this would 95%. And 3 standard deviations out is 99%, as you guys will remember. Silly hypothetical example. Say country Z, we took a random sample of 10,000 people. The mean of men in that particular country Z is 5'2", and the standard deviation is 4 inches. So pretend that that is the truth. And these height distributions, if you look at this versus this, they're very different. So are they is that difference statistically significant? What we're gonna, and I'll show you why or why not. So this, if they're that extreme, that's what I mean by are they extremely different. If results are to the extreme, they likely, just eyeballing this, I would guess that it has statistical significance. But there's a way to tell that. So I'm just showing on the normal curve. So we sampled 10,000 people, so it should probably be on a normal distribution. So this is the US men. I drew a line where the mean of country Z sits. So when you're looking at this particular graph, this is country Z, we're seeing the means in the middle, what you would expect. But if you go over here to the United States, our 5 foot 2 inches sits here on the US distribution. So think of that, this is 2 standard deviations away. So 2.5% or less. So remember, 1.96 is our cutoff for statistically significant results at a 95% level. So that's the most common cutoff. So it's 2 standard deviations away. So yes, our results, there is a statistically significant difference between country Z and US with male heights. So to get more into that information, so as I said, it's about 2 standard deviations away from the mean. So about 5% are on one side or the other, because if you didn't know whether country Z had heights that were, before you sampled, whether the heights were bigger or smaller, you would have to pretend that you don't know if the difference is positive or negative. So that's the best way to do it. I'm going to get more into that later. So you're seeing here graphically 2.5% are to the left, and 2.5% would be to the right if you're looking at 2 standard deviations out. So what this means in like speak that will make sense, hopefully, there is about a 5% chance that the mean and standard deviation would be that different if heights in country Z were not inherently different than the US. So I probably should have worded that differently. This is a little tough going through. So basically, there's a 5% chance that something would, this difference is that extreme that would have occurred randomly. So as I said, with a 5 alpha value or a 95% confidence interval, 5% of the time you're going to get it wrong. It's going to be a random error. And then 95% of the time we're going to get it right. So that's what it means also. So hopefully, and if it's meeting, it's say that difference is 2 standard deviations away, that means there's a p-value of 0.05. And that's the cutoff that you're most of the time looking for. And we'll learn how to systematically check that instead of eyeballing it next week. Okay, so are there any questions about that? Okay. Just for a couple more minutes. So I think I can probably go over this before the end. So that's really what we were trying to get to the entire time. But you'll see all those pieces kind of fit together there. So I mentioned something about one-tailed versus two-tailed tests. So say you're going into something and you don't know whether country Z has men that are taller or men that are shorter. We went in not knowing whether it's one way or the other. So in that case, you would always want to do a two-tailed test, meaning we're looking at a 95% confidence interval, and 2.5% of that 5% random error will be at the left of the distribution, and then 2.5% will be at the right. So we're testing the difference in this case. So that's where it would come in, the difference versus greater than or equal to. So if we're testing the difference, we do a two-tailed. So that is why I put a lot of variations in the language, because they actually mean very different things when you actually implement the tests. So it would be, are the heights larger or smaller? I don't know which one. There are also one-tailed tests. Say I was almost positive that the heights in country Z, given past studies or past work that has been done, I'm really sure that they're smaller than the US. There's no way or very little chance that country Z has taller men than in the US. I go back, I've looked through the literature, and that's pretty established, but I just want to look at the extent of the difference. That's when you would use a one-tailed test. So it only tests in one direction. So that 5% of error is going to be at the left of our confidence interval in that case. So this makes it easier to achieve statistical significance. So if you look up in that table, if you looked up 0.05 instead of 0.025, then you would see that our cutoff for significance is different for a one-tailed test. Instead of 1.96, it's 1.645. So one word of caution, I said why you would want to use it. Do not use a one-tailed test if you can't tolerate a lot of error, because if you're wrong, if you assume incorrectly, there's a bigger chance that you are going to be wrong when you do a statistical test. So if they are actually higher, then you may judge the significance incorrectly, because it is easier to achieve that significance with a one-tailed test. And if you're working with lives, say with a cancer drug, you would never want to do this, because you would want to probably have a 99% confidence interval in that case, because these are people's lives on the line. So you have to keep that in mind when you choose higher or lower. So, all right, so this is really quick. P-value cutoffs, this is what we generally use is 0.05. So 2 standard deviations away when rounding. Less than 0.10 is usually considered marginally significant. Those are the terms that we usually use. And less than 0.01, so 1% error would be considered highly significant. That's just the convention, but it's going to depend on your use case. So nothing magic about 0.05. It's about tolerance for error. How okay are you with being wrong? If I'm wrong, it's not a huge deal. then you might want to use a 90% confidence interval. If you really need to be right, you're testing a cancer drug, people's lives are on the line, then you would want to use something smaller because there's less room for error. Okay, and we'll start there next time. And I can answer questions while I'm packing up if you'd like. Thank you.